So this video is about how we construct ray diagrams to show the formation of an image. So on my screen at the moment, this yellow arrow on the left is my object. This little yellow cross is one of the two focal points of the lens. So as we've just sort of read, if you had light rays arriving from the right hand side of this lens traveling parallel to this line called the principal axis, they'd all pass through that point in space. This is the lens. You can see it's a curved piece of glass. It's curved on both sides. It's probably not quite the right shape. Most programs use the assumption that there's two arcs of a circle squished together to produce a lens, which doesn't actually produce a perfect focal point. That doesn't matter too much. You might just be able to see there's a faint purple line running vertically down through here. This is called the optical axis. So we have the principal axis left to right, the optical axis vertically down. Right there at the center is what we call the optical center. Then there's another focal point on the other side. And this thing over here is an image of this object. Now, really, we should be sort of thinking that this is something that doesn't just appear in space. What we should really have is a screen. So I'm going to quickly switch from that arrow to this lamp. Now, this lamp is supposed to be a point source of light. That is, it's not like a light bulb. It's just got a single point in space where light is coming from. So you can see there's one very particular place for this screen where the circle is a minimum size. If I put the screen too close or too far away, the dot turns into a large sort of diffuse circle. But there's one particular distance where this works nicely. That's different to a pinhole camera. For a pinhole camera, you'd get the dot would stay the same size as you move the screen further back. No, sorry, it would get larger as you move the screen further back, but it would only increase in size proportional to the distance between these two things. The lens here and the design of it determines the distance to the two focal points. So I can change the curvature radius of the lens. If I make the two sides flatter, the focal length gets longer. If I make the two sides thicker, the focal length gets shorter. It was pretty good where it was to begin with. Let's put it back to there. I can also change the refractive index. So if I made my lens out of a material that made light travel more slowly, light gets refracted more, or it gets refracted less. Let's put it back to 1.5 is good for glass. And I can also change the diameter of my lens. Now, if you look at the screen, we start to get some effects because of the diameter of the lens at the moment, except if I find the point where my light is as close to a dot as possible, changing the size of the lens shouldn't really have any effect on what's seen on the screen at all. Now, that's going to be an important rule in a minute. Effectively, the lens collects a certain amount of the light that came out from the lamp and redirects it so that it arrives on the screen. Whether it collects lots of the light or not very much of the light doesn't change where the image on the screen is formed. So at the moment, it's a small lens, so only a small amount of light is passing through the lens and arriving at the screen. Now it's a big lens. Lots more light is being gathered onto the screen. So you might notice the screen gets brighter and dimmer as I change this. I'm not sure you actually can see that. We'll have another look at that in a minute. That's caused by the amount of light that's being gathered together on the screen. So far when we've looked at optics, what we've had to do is study really carefully angles around the lens. Now the glass. So we have to look at the angle of incidence. We have to use Snell's law. We have to work out the angle of refraction. And then for a double refraction like this, you then get to the second surface and have to start all over again. What's nice about ray optics is we avoid doing all of those hard sums and use three principles to work out where the image will form. There's no maths. It's a technique that we use to find out where the image forms. So first thing I'm going to do is click at this thing that says many rays. As soon as I press many rays, you can see that there's lots of light rays coming out from the lens, from the light bulb. Some of them pass through the lens. Again, if I make the lens smaller, we get this sense that less of them are gathered by the lens or more of them are gathered by the lens. Each one at the moment is having its position calculated. If you look closely, you might notice that actually they only change direction right at the center of the lens. They don't change direction twice like they should when we draw this sort of diagram. So they're using a bit of a shortcut in this program to get around a problem. You can see that the light rays are diverging when they come out from the light bulb. That is, they're spreading out, but the convex lens has this effect of making them converge. I can move my lamp around. As soon as I start to move my lamp, you might notice over here on the right hand side, because the incoming rays have arrived at slightly different angles, they've been refracted to slightly different places as well, and I'd have to readjust my screen to find what we call the focus. So we have these two quite similar terms. The focal points of the lens are things that exist and are associated with the curvature and the refractive index of the lens. You can almost imagine for a typical lens, they're these 2 points that float in space on either side of it. But the focus is the place where light from a real object, in this case a virtual lamp, but from a real object, is brought to a single point on a screen. So this is the focus, while this is the focal point. Sometimes this one's called the principal focus. This is the focus. So we have these sort of similar names. Now, at the moment, when we look at these 4 light rays, the top one, the only way we could have worked out where it went is if we used Snell's law and measured angles. So that's not much good. The second one, same is true. The only way we could have worked out where this went is if we used Snell's law and measured angles. But the third one is interesting. I'm just going to move the lamp up a touch. There we are. The third one you can see passes through the optical center. That means that as it arrives and leaves, the 2 surfaces it passed through must be perfectly parallel to one another. Now, we know when you have 2 parallel surfaces, the incoming ray and the outgoing ray are also parallel to one another. Because we're going to assume that all of our lenses are quite thin, what we mean is this distance between the 2 edges is significantly less than this distance between the object and the screen, and this distance, object and the lens, and this distance between the lens and the screen. We're going to say that it just carries on in a straight line. So this light ray at the moment is an interesting one, because actually we could have drawn that light ray. We could have drawn that light ray ourselves just by having a ruler that starts at the light source and carries on in a perfectly straight line. I'm going to move the lamp again to try and achieve something slightly different. No, I'm going to change from the lamp to something else. Well, let's turn that one off. Oops. Oh no, it doesn't work for this. Okay. So that's my first one. Second thing I'm going to do, turn the rays off again, and then I'm going to turn on something called marginal rays. So let's put this thing right near the middle. So at the moment, it's going to take the top of the pencil as being the thing that produces light. I'm going to turn on the marginal rays. So marginal means sort of at the edges. And you can see now, again, I've got the ray that goes through the middle. As we've discussed, that's easy to draw, but it's also showing the rays at the top and bottom edge. These 2 rays are defining the cone of light that ends up being collected on the screen. But also, if I move this up, we suddenly notice here, the top light ray is passing through the focal point on the right hand side. It's just missing it. Let's adjust slightly. There we are. It's passing through the focal point on the right hand side. The reason it's doing that is because it's traveling parallel to the principal axis on its way in to the lens. So any light ray that arrives parallel to the principal axis will be refracted and will travel through the focal point. I'm going to move this again somewhere different. Let's put it down here. My image has gone off the screen, but I'm not going to worry about that too much. Now we're interested in looking at the bottom ray. The bottom ray arrives through the focal point, so on the right-hand side has to travel parallel to the principal axis. So these 3 that we've seen separately so far are 3 light rays that have a position that is set in stone. Whereas when I look at many light rays, you can almost imagine that you could draw these ones wherever you wanted to. And you would have to calculate their path through here. If I choose to draw the principal rays, then there is only one allowed path for each of the 3 rays. Let's look at them all together. The one at the top goes parallel to the principal axis on the way to the lens. You don't get to choose where to draw that line because it has to start at the lamp and run parallel to this principal axis. It strikes the lens, and after it hits the lens, it passes through the focal point on the right-hand side. Any light ray arriving parallel to the principal axis has to travel through the focal point on the right-hand side. Second one, middle one, is one that starts at the lamp and passes through the optical center. Any light ray starting at the lamp, traveling through the optical center, has to travel in a perfectly straight line. And the third one travels through the focal point on the near side, hits the lens, and then travels parallel to the principal axis. These three light rays we can draw without having to use Snell's law. So they're three really important light rays. Now, because of this, we even go a step further, and sometimes we continue to draw these when it doesn't sort of make a lot of sense to. These are the light rays that help us find where the image forms. So something a bit peculiar happens if I reduce the diameter of my lens. You can see while this ray doesn't really do that anymore because it misses the lens, it just carries on in a straight line. It's still helpful to draw it like this because that's how we find out where the image forms. This ray misses the lens, but we still draw it like this to find out where the image forms. So what I'm going to get you to do is have a look at some questions where you have to start some light rays from a particular point in space, and by drawing these three principal light rays, find the point where the light rays cross over with one another, find the focus in each case.